Hi there. My name is Reinier and welcome to this presentation. We're very grateful and happy about Vinduino being part of this virtual conference organized by the Things Network. Thank you guys. You have been proven to be a great resource and supporting team for us. Let me introduce Vinduino to you. So my company provides technical solutions based on LoRa to help farmers improve their crop results. We're based in Southern California, and next to owning a company, I also am a small wine grower. So I would like to start off this presentation with showing you a little video to get you in the mood. This is the vineyard that I was talking about. Here we're walking through. So you see what I do every day, walking the lines, the rows. You can see here that we just had bud break, so the leaves are coming through. Spring is really starting in our vineyard, and that means that we will be irrigating pretty soon. These are the irrigation lines, and here you see buried soil moisture sensors in one of our earlier stations. This is irrigation control for one of our experimental blocks where we test our technology. And here's an example of one of our latest products, which is the 4th generation Vinduino soil moisture sensor station. With that, as an introduction, I would like to start the presentation. So, when we're talking about agricultural technology, we basically also talk about a sustainable food supply. And it may be stating the obvious, but of course, people are concerned about how we're going to feed a growing world population. Key in that whole process is, of course, the farmer. And let's go into what farmers need and want. So first of all, farmers depend on income coming from their crop. So the amount of crop and the quality of their crop is very important for them. Let's talk about crop yield or the quantity of crops first. So when you think about irrigation, you can see here in the picture that irrigation has a big impact on how the crop develops. On the left side, you see grape clusters that were taken from a grapevine that was 100% irrigated, meaning we calculated how much water that plant needed and we provided that. On the right side, you see grape clusters from a vine that was irrigated 30% less than what it needed. And you can see as a result that the weight per berry is about half of the berry weight on the left side. So that's a significant amount of crop loss that you just get because of irrigation. Quality is of course also important. With wine grapes, that's even more important. You can see in Temecula in California that the price per ton could vary between $7,000 per ton in Napa for high quality grapes down to $500 per ton in the more industrial setups. So that's important too. Another thing that keeps farmers awake at night is anything that can destroy their crops. It could be a fungal disease such as powdery mildew, which is shown on the right picture here, or it could be an insect-borne pest like the skeletonizers here. And you can see here they come in teams and they eat the leaves and they leave nothing left. For both pests, there are chemical solutions. So there's a fungicide that you can spray or a pesticide that you can spray. And by following weather patterns and temperature and determining what conditions are optimal for the development and growth of these pests, you can make a pest mitigation program that is very specific. And thus you can save on labor for spraying, but also on chemicals that you use in your fields. Optimizing water use is also very important. Before we used the Vinduino system in our vineyard, we relied on decades-old experience from people who did this for a long time, and you can see here on the orange and red line what our water usage was during the year. And once we installed sensors and were keeping track of soil moisture, we could be more selective in when and how often we irrigated, and as a result we saved about 50% water. After we automated irrigation, and where we basically drive the irrigation times using weather pattern and a calculation that is basically weather based and calculates how much water a plant is using on a day-by-day basis, we could save another 10% of water. So all in all, we saved about 60% compared to the years before, which is significant. On the other hand, you saw from the previous slide that irrigating too much is wasting. Irrigating too little is basically reducing your crop yield, so that's not good too. So the goal is, of course, to optimize your water use. So what does an automated irrigation system look like? And we're including, of course, the LoRa system here as well. You can see here in the fields, in the vineyards, with the rows of grapevines, that we have placed sensor stations in strategic positions. Usually you have one per irrigation zone. Every station communicates directly to the gateway, or base station as they call it sometimes, and then the base station forwards the messages through the internet router to a cloud-based application. The cloud-based application collects the data from the sensors, but it also accumulates data from satellites and a weather station network. All that data combined is used to calculate an optimal irrigation pattern. So you can have that as an output on the screen, but you also can use that to drive irrigation automation. What we have added as a unique feature is we have a feedback system that uses a flow meter or water meters to provide feedback about how many gallons you really irrigated. So suppose the system calculates that that you need to irrigate 1,000 gallons in that field. The water meter feedback should indicate that it's confirmed that you irrigated 1,000 gallons. If you irrigated 10,000 gallons instead, then obviously there's a leak and you want to take action. If it's irrigating much less than that, then something is obstructing the water flow. It could be a clogged filter or anything else, but that requires an action as well. So having a water meter feedback is very important, and we received the World Ag Expo 2019 Top 10 award because of having that feature as a unique solution. When we're talking about requirements for nodes in the field, obviously it's clear that because of agriculture, you need to be able to cover the distance. So long range is important. Low power is important too, because you need to depend on local power or battery power, and it needs to run for a year or longer. So in our case, we have a little battery that gets recharged every day using a little solar panel on the back. And of course, the LoRa technology helps tremendously in covering the distance, but also because it's low power technology, it also adds to the fact that our systems are energy efficient. Of course, when you're out in the field, the enclosure needs to be waterproof, and because you have to deal with people that are not high-tech people in the field, it needs to be easy to install, but also easy to maintain. When we're talking about LoRa technology, one thing comes to mind, and that is that it's 900 megahertz or 868 megahertz in the case of Europe, where line of sight is kind of like a key trait. Ideally, you have direct line of sight between your gateway and your stations. In a lot of cases in agriculture, you're not that lucky. And we found that in all of the cases where we did installations and we didn't have direct line of sight because the stations were behind a hill or in a valley, actually we were able to have reliable connectivity. And the reason why we still can get connections stable without having direct line of sight is because of two effects. One is called reflection, which is easy to explain because the signal bounces around like radar. And another one is diffraction, which is a little less known. But it's in radio propagation terms, it's a well-known effect where if a radio wave passes a sharp-edged obstacle, after it passes that obstacle, it bends down. So for that reason, you will be able to see the signal behind the hill, although the hill cannot be penetrated by the radio waves, but you can still get a good connection. It's not always guaranteed. It's not guaranteed. It doesn't always happen, but so far in our case, we were lucky, I guess. It always worked. So that's basically something I wanted to share because it's very important information. When we're talking about sensors, we should also talk about a correct installation of soil moisture sensors. Here you see the preferred depth. We like to install 2 or more sensors per location, and the reason is that we want to see a vertical soil moisture profile. So we want to see how deep the irrigation water drains. You don't want to drain too deep. If you irrigate very long, then of course the water will basically penetrate deeper. Whereas if you do very frequent short bursts of irrigation, then of course the water will stay shallow. So by managing the amount of water you irrigate per irrigation cycle, you can effectively manage how deep the water goes. And the goal is of course to keep the water in the zone where the roots are actively taking up water, not below. So in this case, for grapevines, water is actively taken up between 2 and 3 feet. And we added another sensor at 4 feet that ideally should always stay dry. If you hit that sensor with water, then you have been irrigating too long and you're wasting water. When you're installing sensors, especially the deeper ones, you may hit a rock sometimes, which is obvious. Then you take another spot where you don't hit the rock. But also in the area where we live here, there is often a hard layer. We call it hard pan, and that hard layer does not water doesn't penetrate through it. So if you install a sensor on top of that hard layer, you may run the chance of water pooling on top of that hard layer and giving you a false reading. It basically indicates to you that there's a lot of moisture down there, but it's not available to the plant. It's just sitting on top of that hard layer and collecting there. Another problem that could happen is if you drill through that hard layer, and believe me, that's hard work, so you know that you're doing that. But if you install a sensor inside the hard layer, water will not reach that sensor, so it will give you a dry reading where the soil above it may actually be wet. So that's not a good thing, and it's just one of those things that we learned the hard way that I'm sharing here to help you avoid situations like that if you're having to install sensors. Once you have installed the system and sensors, of course, customers will ask you what the sensor data means. So there are two types of sensors in the industry that are commonly used. One is the watermark sensor, which is the green sensor on the left. And another type of sensor works on measuring the capacity between two electrodes, which varies with the moisture between the electrodes in the soil. So it's basically the dielectric constant or the dielectric value that changes the capacitance of that particular sensor. The capacitive sensor basically measures the volumetric water content of the soil, whereas the green sensor measures the soil water potential. Soil water potential can be explained as the equivalent of sucking lemonade through a straw. If it's a narrow straw, you need to suck hard. It takes effort to drink the lemonade, whereas if it's a wide straw, then it's relatively easy. And basically, the soil water potential is measured by a tensiometer, this type of sensor gives an equivalent output, which is read as electrical resistance. And there's a table that you can use to calibrate that. But the idea is that if you have high value, it takes a lot of energy from the plant to get water out of the soil, whereas if you have low values of kilopascal, it's basically taking less energy for the plant to get water out of the soil. So both are an indication of how much water is available to the plant, whereas the capacitive, the volumetric water content is not the same as water available to the plant. It depends on the type of soil, whether it's easy to get water out of the soil or hard. If you have a sandy soil, it's relatively easy to get water out of it, whereas clay soil tends to hold on to the water much harder. So you could have a situation where the volumetric water content in percentage is the same, but for the plant it means a difference between life or death. In one case, it could easily get water out of that soil, and with the same percentage value, it cannot get water out of the soil and it will wilt. So it's very important to understand that difference. A lot of farmers like the soil type agnostic type of sensor, the green one, because of this. But both sensors have pros and cons. The watermark sensor is sensitive to temperature and salinity in the soil, whereas the capacitive type of sensors, they're sensitive to density differences in the soil. So if there's an air gap or a rock, it will influence the reading. So that is important to understand about the difference of sensors. Both are useful, both can be used for irrigation management, but both have their own particularities. If you install a gateway, of course, having direct line of sight is good to have, but it's always a good thing to have a high location for your gateway antenna. In the pictures here, you see two locations where we were able to get a high location. On the left is the roof of a winery, where we have a gateway in a waterproof enclosure, and then we have an axial antenna, omnidirectional antenna with 3 dB gain. On the right side, there you can see that we are on a mountain ridge where we could use a location where there was already local power because of a solar panel and a battery, which was used for a radio link for internet access. So we could tap on that power source, and then you can see we use an omnidirectional antenna there. To my experience, the antenna gain is less important. Having a good antenna does make a difference. So an external antenna is always preferred to a rubber ducky antenna that comes standard with the gateway. Omnidirectional versus Yagi does not make a lot of difference to our experience. It could make a difference in critical cases, but so far we had no practical use for directional antennas. If you choose a gateway, I strongly recommend looking for a gateway model that supports Wi-Fi. it makes installation location so much easier if you can move the gateway at a convenient location, whereas if you're dependent on having a cable, Ethernet cable, you have less choices of where you install the gateway permanently. So Wi-Fi is a pro if you're looking for a gateway. With that, I think I am coming to the end of my presentation. Thank you for watching this. I wish you a lot of fun with the other presentations during this virtual seminar or congress. And I also want to thank the Things Industries and the Things Network team once more for allowing me to make this presentation. If you want more information about agricultural technology, especially the technology that we provide as open source, there are several products available. If you want to take the do-it-yourself route, there are printed circuit boards available at tindy.com, and you can program them yourself. If you want to have a product that is ready to go, you can look at amazon.com, look for Vinduino, you'll find us, or go to our website. So with that, I thank you so much for attending this presentation and have a nice day. Thank you.